welcome back. In this video, I'll be going over triple integrals. So yes, we've made it. We went over double integrals and now we're going to be going over triple ones. But first, before we tackle that, I'm going to actually give you kind of a little summary of integrals up to this point so far. So I'm going to go all the way back to one-dimensional. So we're going to start with an f of x with one variable. So I'll put one var. So when this happens, our graph looks something like this, right? And I've gone over this in previous videos. So from A to B, here's our x and y, and some f of x, and we're measuring this right here, the area under the curve. So when this happens, our domain is from A to B, so that would be a one-dimensional domain, so 1D domain. And also, let's see, so this is our f of x, and our integral looks like a to b f of x dx. And what this measures is the area under the curve, right? So we have a one-dimensional domain, but a two-dimensional answer, or a measurement of a 2D quantity. So this is the area under the curve. So we get something that measures 2D quantity. Okay, and that's pretty much it for the one-dimensional case. That's why it's pretty simple, and we only have a single integral, right? So single integral sign. All right, so now let's go into 2D. Then we have an f of x comma y, and this is two variables, right? We were just introduced to this, and our graph here looks something like this. I'll just do a little version of it. Something like that, and here's our surface somewhere up here. Okay, and then we have some domain D down here, right? So this is our domain D, and then we're going to draw straight lines going up until it touches the carpet, right? Our surface, the top here. And this surface is determined by the function f of x comma y. And so we have two variables, and our domain now lies in the xy plane, and it is not one-dimensional anymore, but it is two-dimensional. So two-dimensional domain, because it is determined by both x and y. And so our integral looks something like this. Okay, so we have a double integral, basically, over d in the xy plane, and we have our f of x comma y dA. All right, and as I discussed before, this integral now is not a measure of area, but now it is the volume of this solid created. Okay, so this is a measure of volume, which is technically a 3D quantity, right? If you think of, I guess the simplest kind of 3D object that you can think of is a cube, because it's equal on all sides. But anyways, that's just an example. So measures 3D quantity now. And this, we're using a double integral. Okay, so this is where we've gotten to so far. And the last one, this is the last step we're going to be making in this class, is functions of three variables, and I'm going to introduce the triple integral. So as I said, now we're going to have a function of x, y, z, and so this is three variables, right? And then, so our domain now, if you see the trend, when you have one variable, you have a one-dimensional domain. When you have two variables, you have a two-dimensional domain. And then now that we have three variables, yes, you guessed it, we have a three-dimensional domain. So what this means graphically, so again, I can only draw in three dimensions, or I can only draw or depict three dimensions, because 4 dimensions is, I can't even fathom. And your textbook says the same thing, it's not just me. But anyways, so three-dimensional domain basically means you have some kind of shape, some kind of solid in space, okay? I'm just going to draw like a blob-looking thing, okay? So it's some blob, and this isn't like a plane or anything, it's not flat, so it has mass, well, not mass, but like it has a definite shape. Think of it like a rock, okay? So this is like some kind of rock thing. So this is actually our domain, okay? Um, so this is, yeah, so this is our domain, and they, just for future reference, they usually call this in 3 dimensions. Our domain is W for some reason. I guess because they can't use X, Y, and Z because they're already taken. So they just go to W. And now what our integral looks like is triple integral, because we have 3 variables in a 3-dimensional domain, over W, which is this thing. I'll label it W, this big like rock thing. And then we plug in our function, okay? And then we have dv, and the v here stands for volume. So the differential volume, because the a here stood for area, right? So this is differential area, and now we have a differential volume, okay? And I'll go into the specifics and mechanics of how to do this. Right now I'm just going over the general concept of what doing a triple integral means. Okay, so like I said, this is a triple integral. And the last step here is to figure out what does it measure. Like what is this integral equal to? So one thing, again, we can notice a trend from the first two, is that when we are in one variable, we are measuring a 2-dimensional quantity with our integral. When we were in 2 variables, we measured a 3-dimensional quantity. So yes, following the pattern, when we're in 3 variables, then we're measure a 4-dimensional quantity, which again, like I said, I am not even going to try to depict because I have no idea what that looks like. But anyways, what a common example is, or a common application, common application, I bet some of you guys did that when you were applying to colleges. Anyways, I did too. So, a common application for the triple integral, like what is its significance, what does it mean with relation to this rock, is calculating the mass of an object of a certain volume. So I'll just write down here, just an example would be like calculating the mass. So mass is determined by, it's a quantity that depends on volume. No, it doesn't. Okay, wait, thinking. Well, it's kind of related to volume, so you can kind of think of it like that. But anyways, we'll see examples in the future, so I'll show you how to do that. Anyway, so these are our 3 kind of like summaries of doing integrals with 1, 2, and 3 variables. And I have to say that I wish someone had explained this, or at least wrote this out or something when I was learning this at the time, because I was so confused going between 1, 2, and 3 dimensions, and I didn't even know a 4th dimension existed. And now I'm still kind of wary of it, but apparently it exists. So I've heard from various professors. Okay, so that does it for the summary, and now we'll get into actually executing the triple integral. Okay, so we have our f of x, y, and z, and we're going to integrate it, you know how we, in 2 dimensions, or not 2 dimensions, but with the double integral, the simplest domain was a rectangle, right? Something with straight edges and simple intervals for our x and y. So in 3 dimensions, we're kind of going to do a similar thing to start off with, and what we're going to do is integrate over a box. Okay, so we're going to integrate over box capital B, which is determined by a to b times c to d, and this is just the notation for an interval, e to f. Okay, so this here corresponds to x, this here corresponds to y, and this corresponds to z. Okay, so the way that we would set this up is triple integral over our box b, and you can also replace this with w. It's kind of like trading off d for r with a double integral. Anyways, and then we have our f of x comma y comma z and dv. Okay, and in this case dv, is dv equals dx, dy, dz. Just those all multiplied together. They don't have to be necessarily in that order. You can switch them around. But then if you switch them around, then you have to make sure that their bounds follow. And it gets, well, it's especially important to keep track of what's the innermost variable, I guess, that you're dealing with, the outermost, and the middle one. So we'll see in the examples. Okay, so in this case, x, the bounds on x are a and b, right, as we were given up here. The bounds on y are c and d, and the bounds on z are e and f. Okay, and a through f, these letters, they're all constants right now, because we're starting with the simplest case. All right. So the way we would set this up, so this triple integral is going to equal, and we'll do one at a time. I guess I'll do dx on the outside. So we'll start with a to b. So dx has to, I'm just going to space it out. This is going to be weird spacing, I'm going to tell you right now. I'm just estimating this point. So the x stuff is on the outside, okay? And then I'm going to work my way in. So then next I'll list the y stuff. So then we have c and d, and then dy goes here. So that'll be like our middle variable, kind of. And then we have our z finally. So like that, right? And dz is the innermost. And then in here we, of course, have our f of x, comma y, comma z. Okay? So that's how you would set that up. And this is technically an iterated integral. If you recall from the double integral that we were doing. So iterated just means that you can solve it in steps. So in this case, you just do the innermost first. So you go like this, right? You would solve that through, and you'd get some function of f of x and y. So out would pop some g of x, y. G, I just put g because it's going to be different than what you began with, presumably. So then you get something like g of x, y, and then, here, I'll rewrite it here. Then what we would get is, so then inside the parentheses, I'm going to write g of x, comma y, right? And then this should look familiar because now we're down to a normal double integral, right? And then you would do the same thing, do the grouping, do the inside, and that would pop out some function of x alone. And then we're actually back to single variable calculus, right? So we have h of x dx. Okay, so if this seems a little bit confusing and abstract to you because I'm just using variables, you'll see when I apply it in actual examples with real numbers. So, okay, and then also because this is an iterated integral, one last point is that Fubini, that guy, he's still around. So Fubini says that you can switch around the order. So switch around the dz, dy, dx. You can make it dx, dy, dz or something. Just as long as you keep the bounds moving with your differential. So as I said before, just make sure everything on the outside matches, everything on the inside matches, and everything in the middle matches. Okay, so Fubini's theorem only applies when you're dealing with an iterated integral. So that means iterated is just when your bounds are constants. So when bounds are constants. Okay? And this is kind of the simplest case anyways. So that's good. Alright, so now let's try an example of this. So we have, let's see, we're going to integrate over the box. This is our given f of x, y, z. They're all multiplied together. And then we have a dv. And they give us the box dimensions are the following. So we have 1 to 2 times 0 to 3 times 0 to 1. Okay? So this is what a problem would look like maybe. Something like this. So our f of x, y, z equals x times y times z. Alright, so we'll just plug that in when we get ready to do our formula. So now let's identify what the bounds for each variable are. So x corresponds to the first set of brackets, so that would be from 1 to 2. Y is the second one, 0 to 3. And then z is the final set, which is 0 to 1. Okay, so we can technically do this in any order because all of our bounds are constants, right? But I'm just going to set it up like I did in the last slide. So I'll do the x stuff first. So 1 to 2. And I have to make sure dx is on the outside. So furthest left and furthest right. Okay. And then I'll do the y's. So I'll put in 0, 3 and a dy right inside there. And the last one is 0 to 1, and that corresponds to dz. Okay, and the last thing to put smack in the middle is our f of x, y, z, which is x times y times z. Alright, so now let's start solving. We're just going to start with this innermost integral. And this time, because we are integrating with respect to z, that means that x and y are being held constant. So hold constant. Okay, so as far as the thinking process goes, that just means you can think of these as numbers, right? Okay, so when we do this, we could actually technically move x and y outside of the integral, like right on the outside. Since they're like numbers like 2 or 4, you could just move them right outside, and then z is left inside. So I'll do that in the next step. So 1 to 2, 0 to 3. Everything on the outside of the parentheses, we're just going to consider that as kind of like placeholders right now. They're not really doing anything because we're concerned with what's going on inside. Okay. So then we just copy down the rest outside. Okay, so see what I did here was just move the x times y outside, just because we're treating those like numbers right now, because we are integrating with respect to z. Okay, so then the next step is to actually integrate, so we'll do that here. Then our x and y is still sitting there. Okay, so then we have 1/2 z squared, as z ranges from 0 to 1. Okay, and then we have our dy dx on the outside there. Alright, so now what I'm going to do is just take this 1/2 and move it completely to the outside. And I can do so because I can move the 1/2 all the way to the front, because 1/2 is never going to be a variable in any case. It's always going to be a constant, right? Whereas I couldn't do that with x and y here in this step, because if I moved x and y all the way outside in front here, that would put them outside of the differentials that they correspond to, which is not good, because then you'd end up with variables in your answer, which is that's a totally different like can of worms that we don't want to deal with. So yeah, you always remember, whenever you are moving variables around, when you're treating them like constants, you have to keep them inside of their rainbow. Remember, of the rainbow connecting their differential and the bounds that they correspond to. Okay. So anyways, the point was I was moving this 1/2 out in front, so I will do so. 1/2, and then copy down everything else on the outside here. So what we get on the inside is xy still sitting there. And then we have z squared, which when we plug in 1 squared minus 0 squared. And then dy dx. Okay, so now this this simplifies to 1/2 from 1 to 2, from 0 to 3, and just xy, right? dy dx. Okay, so like I mentioned before, now we're down to a double integral, basically. So now we will integrate with respect to y. So that means our x is being held constant. So this is like a number, like 3. So I'm going to move this x outside so we just don't have to deal with it. And I'm moving it right in front of this integral because I still want it inside the rainbow connecting its differential, x's differential, so dx, and its bounds. So it'll still be inside there. Alright, and I'll write the next step on the next slide. Okay, so then what we get is 1/2 integral from 1 to 2, and then I'm moving x right outside here, and we have 0 to 3, and then a y and a dy and a dx. Okay, so now we'll just integrate like normal. So we have 1/2, 1 to 2, and then x times 1/2 y squared as y goes from 0 to 3, right? We have our dx. So now what I want to do is move this 1/2. We'll have it join the other 1/2 and become a 1/4 outside there. So 1/4 is in the front. We have 1 to 2, and then we have an x times 3 squared minus 0 squared times dx. Okay, and moving along nicely, and this turns into 1/4, 1 to 2, 9x dx. Okay, and now I'll even move this 9 outside, so we make it even simpler. So we have 9/4, 1 to 2 of x dx. And then at this point, we're down to single variable calculus, which we should all be familiar with by now. So this will be 9/4 times 1/2 x squared as x goes from 1 to 2. Okay, and now we just plug in. So these in front, I'll just combine those into a 9/8. And then we have 2 squared minus 1 squared, which is 9/8, times 4 minus 1, which is 3. So our final answer is 27/8. Okay, and again, this is not a volume. It represents some 4-dimensional quantity that the problem didn't specify. It just said calculate the triple integral. So this is still some kind of 4D quantity. All right, so as you can see from that example, by integrating over a box, it was pretty, it might be complicated in a way, but it's not so much complicated as it is tedious, I guess. Just because you have that one added variable, the z, that adds one extra step on to the end. But if you keep your variables straight, then you should be good. Okay, so in the next slide, I'll introduce a new topic.